Welcome. Today we will be in functional analysis. One of the most important results, very basic result and often used result in functional analysis is to know when a nonlinear space is complete. There is a characterization which I usually call an abstract Weirstrass M-test. Okay. In fact, I was the one who had been popularizing that word for that particular result. You will see why. Okay. And whenever we want to show a nonlinear space is complete, this characterization is the most useful one. Okay. For example, I thought of this because I want to do LP spaces in measure theory, and instead of doing it there, I thought I would do it as a separate thing on functional analysis and give a reference to this. Okay. So let us get started. Yeah, before I forget, today is a Pongal, very important day for Tamil people. I come from an agricultural family. I left agriculture and hence cultivation of the fields. But I am in some other agriculture, cultivation of minds, of young, bright minds like you. Okay, that is some kind of a compromise for me. Okay, happy Pongal to all of you. So let X be a non-linear space. I usually shorten it by saying NLS. Okay. So notice that once you have the norm, then there is a metric defined by norm of x minus y. This defines a metric. Metric on x. So when we say x is complete, if the metric space xd is complete, the norm linear space x with respect to the norm is complete when this is complete, right? So what is the definition of this? That means you are, if xn is a Cauchy sequence, I will simply write in x norm, but it's very clear. Okay, then xn is convergent. What does that mean? There is a vector x in x, so that the distance between x and x, which is same as norm xn minus x, goes to 0. Right? Okay. This is the definition of Cauchy sequence. What we want to show is a theorem, but before that, let's try to do something else. Suppose I have a sequence xn in the norm linear space. Okay. Then we have the associated series, infinite series of vectors, infinite series, namely summation xn, n equal to 1 to infinity. I will simply write it summation xn. Okay, what does that mean? So let Sn be the partial sums of the series xk k equal to 1 to n. Notice that these are all vectors in x, right? So if Sn converges to a vector s in x, then we say the series is convergent. This is a series of vectors. Okay, is convergent, and its sum is yes. That is yes. We denote this by, as we do in real sequence or complex series, infinite series of complex numbers or infinite series of real numbers. We note this by summation xn n equal to s. This is nothing other than limit of Sn, where Sn's are partial sums. Okay. So many of you may be wondering, let me just make sure I'm screen sharing. Yes. So many of you may be wondering, okay, already we are talking about a sequence of vectors in a non-linear space, I had a problem with even with R and Rn, okay, vectors and Rn. Now you are talking about that. Is it useful? Have I seen it? Okay, I assure you, you've seen it. You have seen this. This earlier in real analysis. Okay, we are talking about functional analysis, but I am claiming you have seen it in real analysis. Where, recall, if I will just stick to interval, even though any subset will do, or a sequence of function f to r, okay, then we have talked about fn, the infinite series, okay, and we have talked about point-wise convergence and uniform convergence, etc. Right? If I look at only these bounded functions, right? Therefore, B of A, B are all bounded functions. Then this defines a norm. Therefore, this call this as X. Then this X, this becomes a norm. This is called usually subnorm. Subnorm or L infinity norm. Okay. So X with this is a norm linear space. So what you are doing when you talk about this, and with respect to this, in this space, Fn converges to F in this space X norm infinity if and only if Fn converges to F uniformly on AB. Okay. So all these things you can see in my book on consult topology of metric spaces. By yes, second edition. First edition also had that. Okay. And don't worry if you don't remember any of those things, it's all right. The only thing I wanted to assure you is that you have seen infinite series of vectors, right? Namely, when you talked about Weirstrass M-test. In fact, I'm going to recall that that is what the characterization is going to be. Okay, I will say that. So now the next thing is, suppose now we are in a general, back to general case, general non-linear space. Let X this be a non-linear space. Okay, and Xn is a sequence in X. Okay, and let's look at, okay, we say the infinite series is non-convergent, or I'll simply say absolutely convergent if the series of scalars, see, these are all non-negative numbers. Okay, this is a series of non-negative numbers. Okay, this is convergent, right? This is something similar to what we have done. I have a sequence of real numbers. Okay, then I say it's absolutely convergent if this is convergent. Something similar. That's why I call it absolutely convergent, even though this is not very common, uncommon terminology in the context here. Okay, but I usually call it absolute convergence so that it gives an analogy, right? Now, do you remember that any absolutely convergent series is convergent in real analysis or complex numbers? So the first thing we want to prove is the following. If the space, okay, this is an observation, let me call it, let X be complete. Functional analysis people will say this is the Banach space. Let X, no, this space be Banach space. Okay. Yeah. Let Xn be a sequence in X. Assume that this is non-convergent. Then this series is convergent. So what does that mean? This means there exists an S, a vector in capital S, so that summation xk, k equal to 1 to n, converges to S. That means norm of this S minus k equal to 1 to n of xk goes to 0. Okay. This is exactly the way you prove any absolutely convergent series of complex numbers, real numbers is convergent. Okay. Let us quickly recall. Okay. So now I would use x here. So let me just do it similar, because I want to use s for partial sums. It's okay, right? So let Sn be the partial sums. Okay, right? Now what I want to do is I want to show Sn, there exists an S such that this Sn converges to S. Okay, there exists S in X such that this converges. So, but it's a, what we will do is we will actually show Sn is Cauchy. Okay, and hence, since X is complete, okay, there exists an S in X so that Sn converges to S. Okay, so we want to prove Sn is Cauchy, right? So let us assume n is greater than equal to m. Then what is that I have to show? Sn minus Sm I have to estimate, right? But this is nothing other than summation m plus 1 to n of xk now, right? But this is a finite sum, therefore by triangle inequality this is less than or equal to norm of xk. This k is from m plus 1 to n. But notice that what is our hypothesis? Our hypothesis, this series is convergent. So let Tn be the partial sum of the series norm xk, k equal to 1 to n. Okay, right? Therefore Tn is convergent. In particular, Tn is Cauchy, right? Now notice that therefore this one says the following: norm of Sn minus Sm is less than or equal to norm of xk, k equal to m plus 1 to n, but that is nothing other than Tn minus Tm, right? Notice that these are all non-negative terms, therefore Tn is increasing. Therefore mod Tn minus Tm is same as Tn minus Tm, and that goes to 0, right? If you are very pedantic, give me an epsilon positive. There exists n, say that for all m n greater than or equal to n, mod Tn minus Tm is less than epsilon. So for that n, we have this problem. Yeah. So pause, review. See. You see that? I find many students had forgotten. It's more or less they take it for granted. Any absolutely convergent series of numbers is convergent. Okay, but we needed the Cauchy nature, Cauchy completeness of the field, RRC. Here also that's why we have to impose the condition. So the result is not true in any non-linear space. Only if the space non-linear space is complete. Okay, then only any absolutely convergent or non-convergent series of vectors will be convergent. Is that okay? Right. Now, this is the main result of this session. It says a non-linear space is complete if and only if you give me any absolutely convergent series of vectors in the space, non-linear space, it is convergent. Please understand? Yeah, what you have seen is if X is complete, then we have seen this. If you give me any absolutely convergent series, it is convergent. right? Now we are talking about converse, right? Okay, what is given? Whatever be the series, if it is absolutely convergent, then the series is convergent. If you guarantee that, then I want to say X is complete. Is that okay? Right? Now I call this theorem as abstract Weirstrass M-test. I will explain that. Okay. So this is the theorem. So for every sequence x and x, so that the series associated series absolutely are non-convergent, okay, we have the series itself is convergent. Okay, so I call this abstract waste. Why? Recall that what does Weirstrass M-test say? M-test in real analysis. What does it say? It said that if weapon, as I said, a sequence functions so that for each n there exists mn so that modulus fx is less than or equal to mn for all x in AB. This simply means the norm of this, the subnorm of f, okay, is less than or equal to mn, right? And also we are assuming summation mn is convergent. Okay, in particular, what does it mean? Summation of this fn is convergent. Right? Then what we know is the series is convergent. The series 1 to infinity is uniformly convergent in uniformly convergent on AB. But recall what I said is in the space, okay, functions on bounded functions on AB, okay, to R with the subnorm, okay, convergence in here is same as uniform convergence on AB. So the result you proved in real analysis actually shows that this space is complete. That's what it showed. Okay. Pause. Review. Proceed. So unless you have gone through metric space carefully, especially from my book, okay, these things are never done, okay, either in real analysis or metric space. But if you have gone through my things on topology or metric space, you would have seen these examples. Okay. If you don't understand, leave it. I'm going to give a proof of the theorem. But because this is the way you can have some kind of mathematics unified subject. They look different results, but underlying theme is the same. That's what I want to emphasize. Okay, that is the beauty of mathematics. Okay, so let's go back. Let's give a proof. But what is the way to prove? So the first thing is if x is complete, right, and if suppose summation norm xn is finite, that is convergent, then we have proved summation xn is convergent. We had already proved. That's a lemma, right? One way is proved. So then we have to prove the other way around. So what is the other way around? So you are giving me a co-sequence xn. Okay. What is the hypothesis? Hypothesis, you give me any sequence xn so that summation norm xn is convergent. Then the infinite series summation xn is convergent. You understand? This is the hypothesis. It is given to me. Now what are you going to tell me? You are going to give me a sequence xn which is a Cauchy sequence of vectors in x. I have to say it is convergent. Okay, try to understand this. Now this is another secret. Most often when you want to say a Cauchy sequence is convergent, what you do is something very interesting. You bear this well. Okay, at many places you would have done this. For example, real analysis, if you give a sequence of real numbers xn which is Cauchy, the standard classical proof will be to show the sequence xn is bounded, and then you try to find a convergent subsequence of that. Okay, how do I do that? That you do it by saying it has a monotone sequence. But the original sequence, Cauchy sequence, is bounded, therefore the monotone sequence is bounded, therefore it has a convergent subsequence. You understand? Forget it. So one of the important tricks to prove a Cauchy sequence is convergent is don't try to prove it directly, try to find a convergent subsequence. That is the moral of this. Okay, in your analysis you might have done it. Okay, that's what we want to do. Okay, so let's go back. So proof. So if x is complete, then we have shown if xn is a sequence, so that norm of xn is finite, then xn is convergent. Okay, this is already seen. This is the lemma. Okay, over. So let us assume, okay, converse. So what is given? Okay, whenever you give me a sequence so that xn in x, so that norm of xn is finite, then I would, okay, then it means the series is convergent. This is given, right? Okay. So let me just, instead of xn, let me write yn. If whenever yn is a sequence, so that norm of yn is convergent, implies yn, the series yn itself is convergent. Okay. Then what is that to prove? Give me xn, a Cauchy sequence in x. This we want to prove xn is convergent. Right? As I said, the trick is, okay, trick is to find a convergent subsequence. Then you know that any Cauchy, yes, if I have a Cauchy sequence, if I have a convergent subsequence which converges to x, then the original Cauchy sequence also converges to x. These are very standard result, right? Okay. So that's what we want to prove. Now, where will I find this? The only thing I am given is this. Okay. So what we do is we have to find, somehow we have to make use of the hypothesis. Okay, that means I have to find a sequence yn, I'll call it yk, so that norm of yk is finite, and therefore this infinite series yk is convergent. Okay, so the trick is to find a sequence yk in x, so that norm of yk is convergent, therefore this is convergent. This will be automatically convergent. But that means the partial sums, okay, must be convergent. So the trick is I want to make the partial sum to be kth partial sum, that is y1 up to yk. I want it to be something to do with x and k. Okay, I want to find such a thing. Okay, how will I do that? See, once you think of it, it's very easy. So you define y1. Okay, so let us proceed. So since the sequence xn is Cauchy, right? Therefore, what I know is norm of xn minus xm will be as small as 1, right? Therefore, for every k natural number, there is an nk, so that whenever m and n are greater than or equal to nk, norm of xn minus xm will be less than 2 to the power minus k. You understand this? So, in particular, I know that norm of xn minus xnk will be less than 2 to the power minus k for all n greater than or equal to nk. You understand this? Now this suggests how to do that. So I will define y1 to be xn1. Okay, for epsilon equal to 2 to the power minus 1, there is an n1, right? That is xn1. And y2, I will define it to be xn2 minus xn1, right? Therefore, what will be y1 plus y2? That will be equal to xn2. So how will I define y3 then? That will be xn3 minus xn2. And yn plus 1 will be, or yk plus 1 will be xnk plus 1 minus xnk. You understand that? Therefore, what will be y1 plus yk? That will be xn1 plus xn2 minus xn1 plus xnk minus xnk minus 1. So that is going to be xnk. You understood that? So the partial sum, if I look at this yk, this is a sequence in x, the non-linear space, right? And form the associated infinite series k equal to 1 to infinity. Okay, the partial sums. Okay, kth partial sum is yk. Sorry, x and k. Of course, it's yk, but yk equal to x and k. Okay, not yk, x and k. Is it clear? Okay, pause. So if I want to use the hypothesis, or to invoke the hypothesis, we need to establish norm of, okay, this infinite series is convergent, right? But that's very clear, because about now that will be norm of xn1 plus, okay, infinite series norm of x and k plus 1 minus x and k. That is my y k, right? Yeah, that is this is y1, norm of y1 plus norm of y2 plus norm of yk, etc. But these are the thing, and k running from 1 to infinity, right? But this will be norm of xn1 and less than or equal to, and this series, this 2 to the power minus k or k plus 1, whatever it is. Let's not worry about it. Okay. Xn plus 1, what is my assumption? Xn k, that will be less than, yeah, Xn k, right? K equal to, right? But notice that I want it to be subsequent, therefore what I have to choose is at each level, okay, I have to be careful in choosing nk plus 1. Okay, choose nk plus 1, okay, such that nk plus 1 is greater than nk, and for all mn greater than or equal to nk plus 1, I have norm of xn minus xm is less than 2 to the power minus k plus 1. Right? Therefore, my series xn k is a subsequence. You understand? I have to choose nk carefully. Okay. So what I have shown therefore is, okay, we have shown this here is summation yk, this is convergent. Therefore by hypothesis, summation yk k equal to 1 to a infinity is convergent. That means the partial sum, okay, that is y1 to yk, okay, this is my sk, okay, this sequence of partial sums sk is convergent. But we saw that this is nothing other than x and k. This is convergent, right? Hence x and k is a convergent subsequent of the Cauchy sequence. Okay. If x and k converges to yes, then xn also converges to yes. Therefore, we have proved every Cauchy sequence is convergent. Is the proof clear? It's a very simple proof. Usually in a classroom, typical classroom, it is done less than about 5 to 7 minutes. But I wanted you to enjoy what are the concepts involved, how it's related to what you have already learned in real analysis, and on the way we also picked up some important insight, trick, or a principle. Whenever I want to show as Cauchy sequence is convergent, then try to find a convergent subsequence. Okay. For example, you would have used it in Arzi-Ascari theorem. You would have used it in piano existence theorem in ODE. Okay. So you can see the mathematics is beautiful. If only I pay attention and try to see the scenery. Okay, it's okay. Just the video is short, so let me just give some analogy. Like most often nowadays, when you want to go on a tour, okay, on a vacation, what you do is you are worried about taking pictures, taking selfies, but you don't go and just enjoy the place. Okay, watch the beautiful things, the change in culture, the change in food habits, the way people speak, okay, they behave, and the scenery. There are a lot of beautiful things to watch. You don't do that. The similar thing happens in mathematics. Okay. Whenever I learn something, there is only one thing, like taking selfie, I have to attend exams. Okay. So you don't enjoy mathematics. Okay. But my purpose is to make you believe, make you enjoy mathematics. I hope you enjoy it. We'll meet again. Take care. Stay safe. Once again, happy Pongal.